Thank you, thank you. Okay, as you already heard, my name is Marija, and I work as senior ZK researcher in team 3227, which is part of Attic42 company, and also I work as assistant professor at Faculty of Mathematics in Belgrade. And also I'm head of department for differential equation at the same faculty. But also, I'm co-founder of Mathematical Academy, and Mathematical Academy is some kind of private school where we are working with talents in the field of mathematics, physics, and cryptography. And for example, this year our talents, best of them, obtained 41 medals on the state competition. So we are very proud of them. And for example, last year with cooperation with Attic42 and Ethereum Foundation, we organized probably the first zero-knowledge proof course on Balkan. So let's start. Today's topic is ring and module learning with errors, stealth address protocols. So today we will talk about post-quantum cryptography and, of course, private transactions. So let's start. First, we will talk about private transactions. You know that blockchains like Zcash and Monero have some cryptographic methods at their core that enables privacy of transactions. But there is a great need to introduce private transactions on the public blockchains, such as Ethereum. So, when we talk about privacy of transaction, what we mean by that? Maybe we want to hide the amount of transaction, but maybe we want to hide the recipient address, maybe sender address, but maybe we want to hide all three things together. Or maybe we just want to hide one of them. Okay? And we can do it. We can use different cryptographic methods. For example, we can use zero-knowledge proofs like Zcash. We can use ring signatures, stealth addresses like Monero. Or, for example, we can use fully homomorphic encryption. And today we will talking about stealth addresses, and with stealth addresses we want to achieve that we want to hide the recipient address. So we want to have the same structure as we have today, and we want to hide the recipient address. In order to achieve this, we want to have this structure. So we have the recipient, Bob, and we have Alice. Alice will be sender. So first, Bob needs to generate some kind of stealth meta address, and he will send this stealth meta address directly to Alice, or he will add this stealth meta address directly to some registry. And after that, Alice will find this stealth meta address of Bob. She will perform some operation, and after that, she will calculate new address of Bob, and she will send the money to this new address. And after that, Bob is able to control the assets from this address. This is the general idea, okay? So, when Bob's add stealth meta address to this registry, everyone can send the money to Bob's new address. Every time, Bob's will generate new address, stealth address, okay? And we can achieve this using different cryptographic methods. The most known is dual key stealth address protocol, which includes Diffie-Hellman approach. So, in order to obtain the address, sender and the recipient will calculate this address in a different manner. They will use share key, okay? And also they will use some other things, but important here that we will have multiplication of scalar and point on elliptic curve and hashing. And we can achieve to obtain this using different cryptographic methods. For example, here we can use elliptic curve pairings in order to achieve this. And these two protocols are results of work of my colleague Mikhailo and me, and we created two new protocols that using elliptic curve pairings. One protocol using single key and the second one using dual key. And we obtain really good implementation results. And those protocols above are really great protocols, but they are not quantum resistant protocols. And if we want to have quantum resistant protocols, then we need to use different technique. So we use ring learning with errors and module learning with errors technique in order to obtain stealth address protocol that are quantum resistant. And these two protocols also created Mihailo and I. And today we will talk about these protocols. And in order to obtain post-quantum security, we can also use fully homomorphic encryption. And what was our motivation to do this? Well, we read the paper based delta address protocol that was written by Vitalik and Tony, and they use Diffie-Hellman approach. So they use dual keys delta address protocol, and they already implemented some things like these contracts. They use dual keys delta address protocol, this elliptic curve, and also view tag. View tag is here just for optimization reason. But also, we can see on top of this, they wanted to have different schemes that using elliptic curve pairings and, of course, lattice-based schemes. So they want to have post-quantum schemes. And this was our motivation. Okay, so now, in order to understand our protocols, we need to explain the basic concepts. So we will start with math, but we will talk about only basic concepts, so we won't hurt you, at least not much. So let's start with learning with errors. But before this, we need to go through technique learning without errors. So we want to explain why we need to add errors. You know that when you have your private key, usually today you obtain your public key as a result of multiplication your private key with generator point on elliptic curve, okay? And when someone wants to calculate your private key and he's knowing your public key, he needs to solve discrete logarithm problem on elliptic curve. And this problem cannot be solved in real time for our computers. But quantum computers can solve this problem. So, in order to calculate public key from private key, we need to use different technique if we want to have post-quantum security. So, let's start. I think the best way to understand something, it is to use this on example. So, we will start on example. And here in this example, we have Mihailo. And Mihailo has some secret vector. And this secret vector will be Mihailo private key, okay? In order to obtain public key from this private key, Mihailo will multiply this public matrix A with his private key. So we can see here, this is the first column of our matrix A. This will be the second column, third, fourth. And this is the first coordinate of our secret key, second, third, and fourth. So this result here will be the vector, and this vector will be public key of Mihailo. Okay? So it is easy, very. But now, if someone wants to solve this problem and find the private key from the public key, he needs to solve the system of linear equations, and this equation will be here will be x, here will be y, z, and t. So we will obtain 9 equations and 4 unknown variables, okay? But we know that there exists a solution of this system of linear equations, and the solution will be private key. So instead of considering this system of equations, we can consider system of 4 equations. So we can choose the first 4 equations and obtain this system. And this system is system of linear equations. And I think that everyone here in the room know to solve this system. So we can use Gaussian method of elimination, or we can use Cramer rule, okay? So we can solve this. And this algorithm is not secure because we can find Mihailo private key using Mihailo public key, okay? And because of that, we need to add errors. So now we want to explain technique learning with errors. So let's start. We will have the same example as we had before. And now, in order to calculate Mihailo's public key using Mihailo private key, we will multiply the public matrix A with private vector, this little s. And then we will add errors. So the left-hand side is the same as we already had in the previous example, and we will obtain, this was the public key from the previous example, and now we add some numbers, and these numbers are errors. And what are these errors? So we will choose some numbers from some range. Here in the example, we use numbers from the range from -5 to 5, okay? And we choose random values, and only Mihailo knows these values, okay? So if someone wants to calculate Mihailo new public key, this will be after we add these errors, he needs to solve this system. Now we have 9 equations and 4 unknown variables. So we will obtain this system here when we add errors. And this system here probably does not have solution. You can try. I did not solve this. But why? Because we have here 9 equations and 4 unknown variables. And if someone wants to calculate Mihailo private key using this public key of Mihailo, he needs to solve every system with every possibility. So here we need to add -5, -4, -3, and so on, and every equation. So we will have a lot of possibilities, and we need to solve every system here. So if we have a private key that has a lot of coordinates, we will obtain so many possibilities that our computers cannot solve this problem, but also quantum computers. So this is the idea. And in order to obtain even harder problem, we can use modular arithmetics. So here, in order to calculate Mihailo public key, we will use modular arithmetics. So we will divide this number 2856 with number 89. And the remainder of this division will be 11. So if you are looking now this system and we obtain these values as Mihailo public key, I think that you can agree that probably no one of you cannot solve this problem in real time. So this is idea. And we talk that we will use technique ring learning with errors and model learning with errors, but we talk only about technique learning with errors. So why we need to add ring? Because, for example, if we consider this problem is problem that we already saw, that when we are using technique learning with errors, we have here, in order to calculate one coordinate on Mihailo public key, we have scalar multiplication of one row of matrix and private key of Mihailo, okay? And we want to have some magical operation here to obtain cheap product operation. So in order to obtain this, we will use ring of polynomials. Why? Because we can use fast Fourier transformation in order to calculate this in fast way. So because of optimization reason, we will choose to work with ring of polynomials. So when we say that we are working with ring of polynomials, that means that we are working with polynomials that has degree that is less than d, and of course we will calculate coefficients modulo q. So we have modular arithmetics, and degree of polynomial will be less than d. Okay, so here will be work. We will work in this space. So let's start. The first that we need to mention here is that these techniques, learning with errors, ring learning with errors, and model learning with errors, are similar techniques, because when we are first, we need to have this equality to hold, and when we are using learning with errors, we have this. So we will not have polynomials, but we will have system of equations. But when we are using ring learning with errors technique, we will obtain polynomials, but only one equation. And when we are using a model learning with errors technique, so we will have, for example, columns, and in these columns we will have polynomials. So this will be the mix of that. Okay, so we will have system and we will have polynomials. Okay, and now in order to calculate some stuff, we want to explain how we can do addition and multiplication on polynomial ring. So in this example, I want just to show you how we calculate the result of addition of polynomials f and q. So if we have that this is polynomial f and this is polynomial q, then we will obtain this using high school math. Yeah. But now, because we will working with modulo 5, this number here, 8, will be number 3. Okay. And this is easy. And let's multiply them, and we will obtain this result. But here, we can go back and see. So we are working with ring of polynomials. So when we have x to the degree d and add 0, that result needs to be, add 1, that result needs to be 0. So here, x to the fourth, because fourth is n, will be minus 1. So here we have minus 1, and this 8, because we calculate modulo 5, will be 3. So when we have x to the power of 5, we will obtain x multiplied by x to the power of 4th, and this is minus 1, and because of that we obtain minus 6. And 6th is 1 because we calculate using modulo 5. So this is very simple. And now we can explain our protocol. So we want to have the same structure as we already had. And we have recipient here, Bob, and we have sender here, address. And we already said that first thing that Bob needs to do, he needs to generate some kind of stealth meta address. Okay, so in order to do this, Bob needs to calculate his private key. And in order to calculate public key, he also needs to add errors. So Bob needs to calculate private key, and private key will be this little k, and then he needs to calculate these errors. He will choose these errors. He will multiply this public. When we talk about ring of polynomials, this will not be matrix. This will be polynomial. So we will multiply polynomial with polynomial and add polynomial of errors. Okay, but coefficients in this polynomial will be very small numbers. So we will calculate this public key and add this key in this registry. And this little v will be viewing key. And viewing key is here just for if you, for example, have tax inspector and you want to prove to them, to your tax inspector that you pay all taxes for all your transactions, then you need to give him viewing key. But if you don't need that, then we don't need to use this key. So, and because of this, we call this key dual key. So, okay, after this, we will add this in this registry, and the sender will go to the registry and find this public key in the registry. And after that, he will generate, Alice will generate her pair of keys. So in order to calculate her public key, she needs to calculate public key in a way. She will multiply public polynomial with her private polynomial and add polynomial of errors. Okay, and she will obtain this, and this will be Alice's public key. And she will put this public key in this ephemeral public key registry. Okay. In order to calculate the address of Bob, what she needs to do? She will multiply her private polynomial, private key, with a public polynomial public key of Bob. Okay, and we know that Bob will be calculate this share key in a different manner. So he will multiply his private key with public key of Alice. And this is technique Diffie-Hellman. But here we know that we add some errors. So Bob only knows his errors and Alice only knows her errors. So when we multiply these things, we will not obtain the same result. We will obtain the same result if we are using dual key stealth address protocol without errors. But with errors, we will obtain different result. And because of that, we need to find a way that both of them obtain the same address. And we can do two things. The first thing that we have here on the slide, we need to cut off the lower bits of every coefficient in order to calculate the same address. So, in order to calculate the same shared key. And there is different way, and we can use it to calculate that both calculate the same result, but in order to do that, we need to use some advanced math. And here we will use just cutting off lower bits. And after calculating of the share key, well, this will be the public key of new address of Bob. So Alice will multiply public polynomial with the shared polynomial and add public key of Bob in order to calculate address. And then she will send the money to this new address. And Bob will have private key for this new address, and this private key will be result of addition of his private key for his stealth meta address and the share key. And of course, we know that we will obtain the public key as a result of multiplying this polynomial private key with public polynomial and add error. So this will be the address of Bob, and Bob knows private key for this address. And we know that if someone wants to calculate private key from this public key, well, if we choose that Bob's private key has a lot of coordinates, he cannot do it, even if he had quantum computer. So it is safe. We have secure protocol, and in this protocol, no one cannot know that Bob, except Alice, that Bob received the money. So this was the first protocol, and the second one using model learning with errors. So we will have columns of polynomial, and how we do addition here. Well, in the same way as we had using ring of polynomials, but just in one row we are using technique that already used, and in different row using the same technique. So everything is similar, and also multiplication here is going on the same way as we already talked about. So we will obtain second protocol that are using model learning with errors stealth address. And here we won't go to details because everything's look so similar. And we just need to add some vectors in order to have same dimensions, and nothing else cannot be changed. So in order to obtain this model learning with errors, and why we are doing this, because we can use some implementation result for this technique, model learning with errors, and because of that we are using this approach. And for the end of this talk, I want just to mention some things. I want to mention that fully homomorphic encryption, the holy grail of cryptography, are using this technique, ring learning with errors. So if you understand this, you can work with fully homomorphic encryption. And why fully homomorphic encryption is important? Because, for example, you can perform some operation over encrypted data and obtain the encrypted data. And whoever working on this does not need to have decryption key. So your data are safe, and only user can decrypt the data, and if user performs the same operation, he will obtain the same result as a result of decryption of this. So it is very important to use fully homomorphic encryption when we have some sensitive data. And you can think now how you can use this our approach with ring learning with errors and model learning with errors in order to create protocol that is stealth address protocol but using fully homomorphic encryption. It is very easy, and you can think about this. And this is everything for today. Thank you.
Do we have any questions in the audience? Feel free to ask. Yes, 1 second.
Yeah, thanks for the talk. I hope that this isn't a stupid question, but this stealth address protocol only works if Ethereum also supports something like dilithium, and so it's not working with ECDSA or anything like that. Okay, thank you.
So I just want to say there's no things as stupid questions. Like no one's gonna think anything of you, even if you ask something that's stupid. We're here to learn things, so feel free to ask questions, ask the things that you don't understand. That's how we're gonna figure out things together. With that being said, any more questions? Oh my God, there's 10 hands in the back. Whoa. I'm just kidding. So feel free, last call. Sold. Marija, thank you so much for an amazing talk, and it was a pleasure, as always, to have you as a speaker. Give it up one more time for Marija.